So, today we will discuss a different type of neural network. We have discussed feed forward network, back propagation network, which is normally multilinear network, also radial basis function network. Similarly, another kind of network we considered is recurrent network, but today's network will be a little different, which will talk about self-organizing map, and specifically we will only focus on Cohen feature map. Cohen self-organizing map. So, today we will be discussing about the self-organizing map, specifically Cohen. So, we talk here. So, the specifically we will be considering only Cohen network. We will discuss what is Cohen sum learning algorithm. We will simulate some examples. We will also show some actual simulation. We will talk about clustering in a visual motor coordination and summary. So, self-organizing map, obviously this is motivated by certain features in the brain as usual. In this case, the neurons are organized in one or multidimensional lattice. So, 1D lattice, 2D lattice, 3D lattice, we can think of even higher dimensional lattice also, from because in engineering application we can even become a little more abstract. The neurons compete among themselves to be activated according to competitive learning scheme. So, there are many neurons in a lattice. They are excited by the same input vector or input feature or input whatever data you can say, and all the neurons in this space, they are in the lattice, they are all excited simultaneously, and there is a competition. And the weight vector associated with the winning neuron is only updated in the scheme winner takes all. So, that is, if for example, I have a 2-dimensional lattice, imagine I have many neurons placed in this. So, when an input excites this lattice, one of these neurons gets becomes the winner. Then in the winner takes all in this scheme, only the weight associated with this neuron are updated, is updated. Whereas there is another scheme that is being employed is softmax rule, where not only winning neuron, also maybe the nearest neighborhood neurons, they also get updated. The weights associated with those neurons also, they take part in decision making process. So, that is the principle. So, this is in general a self-organizing map, but Cohen, he proposed a novel neighborhood concept where the topology of input data space can be learned through sum. That is, for example, a data that is coming from which kind of geometry, thus that can be understood or that can be captured through this sum, self-organizing map. So, in the scheme, a neural lattice can be one or multidimensional as usual. A neighborhood concept among individual neurons in a lattice is a priori embedded. As neurons update their weights upon computation, a meaningful coordinate system for different input feature over the lattice is developed. We will see how this happens in Cohen network soon. So, this is a 2-dimensional Cohen lattice, where you are seeing the neurons are all spread over, and this is your input vector x, which is n dimensional vector. This excites all the neurons. Okay, as the data comes, all the neurons are excited, and each neuron as usual is associated with a weight vector wi. Each neuron is associated with the weight vector wi, which is also n dimensional, A specific neuron wins based on some distance measure, which is a function, some kind of function between a distance measure between x and associated weight vector with a specific neuron. So, based on that, a winner is declared, and normally this distance measure, when it is minimal in a specific case, that specific neuron is declared as winner. So, once we understood the principle, now we will talk about the algorithm. So, obviously, as you saw that we can have one dimensional neural lattice, 2 dimensional, 3 dimensional, and all the neurons is associated with a weight vector which has same dimension as that of input vector. And then before we start the learning process, these weights are all associated with some random weight vector, and this random weight vector has nothing to do with the actual input data. It can be anything, okay, from anywhere. And so 3 things are involved in the SOM algorithm, self-organizing map learning algorithm. First step is computation, that is, we find the winner. To find the winner, cooperation, that is neighborhood, the winner selects its neighborhood, and finally weight update. So, computation is we take some kind of distance function, a function of a distance measure, and for all neurons we compute this function. The neuron for which this function is minimum is declared as winner. Let m is the dimension of the input data space and weight vector. So, that is the weight vector and input data vector, they have all m dimensional. Let a randomly chosen input pattern is x. We select this input pattern randomly, is given by this vector x, which is m dimensional, you can easily see. And synaptic weight vector for neuron j, which is wj, is wj1, j2 up to jm. And the best match of the input vector x with the synaptic weight vector wj occurs where the Euclidean distance, this is just one measure, it is not necessarily, and there are many also some algorithm they use a different distance measure, but today you simply understand, because we are all aware of Euclidean distance. So, we compute Euclidean distance between the input vector and the weight vector, and for that neuron where this distance, Euclidean distance, is minimum, we declare that neuron as winner. So, let I index to identify neuron that best matches x, that is that I x is actually the winning neuron index for the winner. Okay. So, obviously, this is the over j, where this is this quantity is the Euclidean distance measure. So, this Euclidean distance is minimum for a specific j, and that j is actually I x for the winner. The winning neuron selects its neighbors according to a predefined neighborhood function. This is called cooperation. That is, as I told in the beginning, that winner takes all scheme where only winner takes the final decision, whereas in softmax rule not only winner allows to be cooperative, that is, it allows its neighbors also to participate in decision making. So the winning neuron selects its neighbor according to a predefined neighborhood function. Let Hji denote the topological neighborhood centered on winning neuron I. So that is, this is my winning neuron I, and this is the typical neuron J, and distance between this is Hji. So any neuron around this winning neuron, the distance from the winning neuron I is Hji. Dij denote the lateral distance between winning neuron I and excited neuron J. So there are two things that Hji denote the topological neighborhood centered on winning neuron, and Dij denote the lateral distance between winning neuron I and excited neuron. These two things. Okay. So that is, for example, I have a lattice here. This is my winning neuron I, and this is my jth neuron. So they have a lattice distance. Within the lattice, the distance is Dij, whereas the topological neighborhood, that is how close this neuron with this neuron, that is defined by a function Hji. So obviously Hji is a function of Dij or Dji, whatever you say. That's all right. So you hopefully you are very clear about the lateral distance, that is the absolute distance between a neuron, between any two neuron I and J. Whereas Hji defined the notion of neighborhood, that is how close this neuron to this neuron compared to other neurons. This is a kind of a function. So this is a function of Dij. Okay. So topological neighborhood Hji is symmetric about maximum point defined by Dij is 0. That is, when distance is 0, lateral distance, that is when the neuron for which we are updating the weights is same as the winning neuron, obviously the distance between winning neuron and same is 0, and for this Hji has to be maximum, and we can say that is 1, and h, the lateral distance increases, Hji becomes the function Hji tends to 0. All right. So in other words, it attains the maximum value at the winning neuron I, for which the distance Dji is 0. The amplitude of topological neighborhood Hji decreases monotonically with increasing lateral distance Dji, decaying to 0 for Dji tends to infinity, which is a necessary condition for convergence. Okay. So I hope you understood that if Dji is 0, then Hji is maximum, and as Dij tends to infinity, Hji becomes 0. So a typical neighborhood function Hji is a Gaussian function. There can be other functions also, but one of the very typical is a Gaussian function. So when Dji is 0, it is maximum value is 1, and as it goes to this direction on the other direction, the value decreases finally to 0. So normally this function Hji is exponential minus Dji square by 2 sigma square n, where sigma n is defined like this, the width. So, what is meaning of this? If you can see this, when the n is the specific learning step, in the beginning n equal to 1. So, you can see when n equal to 1, this value becomes almost like 1. So, in the beginning sigma n is sigma naught initial value, but when n increases and the highest values 10,000, 50,000 iterations you go, then this value will become almost 0. So, sigma n goes to 0. So, what you are actually trying to do is that using this kind of function, what you are saying in the beginning, if you take this kind of things. So, in the beginning what happens when a neuron, because nothing is the neural lattice knows nothing about the input data. So, in a sense almost all the neurons in the lattice is considered as a neighbor for the winning neuron, but as learning progresses the neighborhood decreases. That is the meaning of this. So, meaning is as learning progresses, the neighborhood shrinks. That is the idea of this neighborhood function. Now, you can easily, I will give you some example of what is the lateral distance. For example, this is a single 1D neural lattice. 1D lattice. So, in this lattice, let us, this black is the winning neuron, and I want to compute what is the lateral distance between this red one 2. So, obviously, this is the absolute magnitude between 3 and 2, which is 1. Similarly, the distance between 5 and 3, we can say this distance measure, the lateral distance is 5 minus 3, the absolute value is 2. So, like that. This is an example of 1D lattice. Similarly, the example of 2D lattice also we can see. In 2D lattice we talk about in terms of position vector, and then the example is like this. This is a 2D lattice. So, you can easily see this, if this is the winning neuron, this is the winning neuron, and this is the neuron for which we want to compute the lateral distance. Obviously, the position of this neuron is 3 2 or 2 3 you can say, and this is 4 2. So, obviously, the index of the winning neuron is 2 3, and the index of neighborhood neuron, the red one, which is 4 2. So, this is the red colored neuron. So, obviously, the distance between these two is 4 minus 2 whole square and 2 minus 3 whole square, and this is 4 minus 2 whole square is actually this is should be distance like this. So, 4 minus 2 whole square, that is 2 square is 4, 2 minus 3 whole square is 1. So, root over 5 is the lateral distance. Okay. Once we understood this preliminary concept, then the Kohanen proposed this algorithm. This is the Kohanen algorithm. Okay. So, this Kohanen algorithm, what you are seeing is that this is your the weight for a specific neuron that is being updated at any instant is this is the learning rate, this is the neighborhood function of the jth neuron corresponding to the winning neuron, which is Ix, and this is the input vector, input data x, input vector x, and this is the weight associated with the jth neuron. So, you can easily see if this is 1 for the winning neuron, then what is actually happening is that x, that is w is actually closing towards x, that is that specific weight is moving towards the specific input vector. And so this is a specific standard one. So, weights associated with the winning neuron and its neighbors are updated as per a neighborhood index. Winning neuron is allowed to be maximally benefited from this weight update, while the neuron that is farthest from the winner is minimally benefited. So, that is the idea of this neighborhood function. Okay. And also we make sure that the learning rate in the beginning is maximal, the value, and as the learning progresses, its rate becomes very small. Okay. So, this we have already talked about. So, this equation that we talked about, this is our normal Cohen learning algorithm. So, this equation will move the weight of winning neuron Wi towards the input vector x. This is very important. This equation will move the weight of the winning neuron Wi toward the input vector x. So, maximally, whereas its neighborhood will go towards x according to the distance from the winning neuron. So, the objective is that how, like now normally the input data, input space is infinite. So, the objective of SOM or self organizing map is that how can I represent a voluminous data or infinite data, number of data using finite number of samples. This is the basic idea behind this competitive network, and this is also in classical terminology. The specific thing is known as how to form clusters, and we have already learned clusters are used in pattern recognition, in image coding, in image processing, many other things we use clusters, specifically pattern recognition. So, now once we understood, so what we understood until now is Cohen lattice, that lattice can be any dimensional, 1D, 2D, 3D, and there is a competition once they are excited, one is winning and the others are its neighbor. In the beginning the neighborhood is very large, as the learning progresses the neighborhood becomes shrinks, that is the idea, and finally the objective is that Cohen showed that such scheme preserves the topology of the input space. We will see that now. Now, here what you are seeing is that 1D SOM learns 2D topology, that is I have a 1D neural lattice, a neural lattice which is 1D, like for example, if my neurons are placed in a line. So, this is a 1D. Now, I will excite this 1D lattice with data from a 2D structure. The 2D structure can be a square, can be L-shaped, can be anything, triangle. Now, can I say that this 1D lattice can actually preserve the topology? Can it tell me after I form the clusters using this 1D lattice from the data that is coming from a 2D topology or 2D geometry, then can I say that looking at this weight vector of 1D lattice, can I conclude something about the structure of the 2D input space? So, this is what is the question. So, my input space is a square. So, that is a perfect square I take. So, this is a perfect square, say 1 meter and 1 meter. So, my data is coming from randomly from this square, I do not know, and I excite this data, I excite this 1D lattice with this data. Now, looking at this the weight vector of this 1D lattice, can I conclude my data is coming from a 2D lattice which is a square structure? This is the question. Now, we will do that simulation to let you know what actually is a coherent lattice, a coherent sum. So, a 1D coherent lattice with 100 neuron is selected. So, I selected a 1D lattice with having 100 neurons. So, since each data point is 2 dimensional, because any data here has x coordinate and y coordinate, and obviously the weight associated with each lattice, each neuron of this lattice also will be 2 dimensional. So, x is 2 dimensional. So, also W j is 2 dimensional. So, training is done for 6000 iterations. Now, for this the dimension is m equal to 2, x is 2 dimensional vector, each weight vector is 2 dimensional. Now, weights are all randomly initialized for the lattice. So, the first element of all weights were lying between 0.4 to 0.4, minus 0.4 to 0.4. So, also the second one minus 0.4 to 0.4 is all randomly distributed. The input x is uniformly distributed in the region 0 to 1 and 0 to 1, all right. That is my input space is actually 0, 1, 1. So, this is my input space, my data is coming from this space, whereas my weights are initialized. This is minus 4, 0.4 plus 0.4, okay, and also this is 0.4 and this is 0.4. So, this is like this. So, my weights are all confined to this zone, the weights of the 1D lattice, whereas my data is actually coming from here. Now, we will see what is happening. So, this is my input space, random data, and this is the initialization of the weight. You can easily see, this is sorry, this is from 0.04 to 0.04 and 0.04 to 0.04. So, very small zone around the origin, all the weights were all trained, initialized. So, obviously, the weights have no value. So, this is a mistake here, it was I showed you. So, this is a not 0.4, this is 0.04. To let you know why we have taken very small value, just to show that you can start from any initial value for the weight, and still you capture the topology using this coherent lattice. Okay. And after 6000 iterations, surprisingly, if you plot the weights sequentially, that is, for example, I have this is my sequence of 100 neurons. So, I plot this one, then this one is this one, this one is this one, and this one is this one, like that. If you look at it, has developed a structure in such a way, by looking at I can easily see that this exactly, a 1D lattice captures a 2D topology. So, you can see that this 1D lattice which was confined to a very narrow zone around origin, it expanded itself, it expanded itself, the neurons, and they spread in such a way, the weights were so organized that they it captured the 2D lattice. I will show you in a movie style now how this actually looks like. So, you see that that how this 1D lattice, which was you said one line in the beginning, and slowly it is developing to a very nice structure and telling us the data is actually coming from a square. All right. I hope you could appreciate that. Again, just to let you know what is exactly, those who could not follow it again, I will again repeat it. So, you see that in the beginning, you know, if you look at the structure, the lattice is actually taking this shape, or it's spreading it to let us know the topology is a square 2D. Okay. So, now we will take okay, that was a square. You may say okay, it's all right, where it's nothing surprising, but now we will take a L-shaped input space. L-shaped means this is my L shape. So, my data is not coming from a square, but it is coming from a L shape. And can I tell that now if I train if I update my weight of a 1D lattice, that is again I have 100 neurons in 1D, and they are again in a small, again this is not 0.04, 0.04. Okay. So, the weights are randomly initialized. So, can I say once again once they are trained, they will give me information that topology is from actually the input space has a topology of L shape, just looking at the weights of this neuron, can I tell. And in fact, this is also true here. So, this is my input space, the data is all randomly generated from this L shape, and this is my small weights, initial weights 0.04 to plus or minus 0.04, the range, and then you see that after 6000 training step, again the weights, if you look at the weights, they have exactly L shape. You can easily see, if you easily see the topology of the input space must be L shape. Well, when looking at the data, you can infer. And again, I can show you a video on this. So, this is a L shape, the input data, and unlike the other one, which was rectangular, now it is L shape, and you see that how surprisingly the things are moving in a different manner. See, this is L shape, and finally those who could not capture, for them I again help it to show that how actually the neurons they self organize themselves in such a way the topology can be we can say the input data is coming actually from a L shape using 1D lattice. So, you see that the first part is already, this part is L, and again suddenly this is spreading to say that this is L shape. Okay. So, that is something nice to see. You can all do it in your sit in front of your computer, write the program, simple program. You can write in C or MATLAB, and you can have fun with this kind of structure to learn that how topology of the input space can be actually recognized using this self organizing map learning algorithm, specifically only specifically Cohen lattice. So, now we will use, earlier we used 1D lattice, now we will use 2D lattice, and again we will take the same input space, and we will see how in 2D case it varies. Okay. So, again the square input space, the input space is the structure is square, and so we take again 2D Cohen lattice. So, 10 rows and 10 columns, and with that you see that the weight space is initialized in very small value, and so this is my input space, this is my initial weight, very small weight around origin, and after training is over, you can easily see that they are very regularly arranged, and these neurons in 2D neurons in such a way you can easily see that topology is a square. So, this neurons, this we have plotted, this is neuron 1, neuron 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Similarly, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, like that you can easily see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, what you are seeing is that we have plotted every all the neurons in the neural lattice, and they exactly occupy a space perfectly distributed in such a way the topology is now regular and it looks like a square lattice. And this square lattice will even look better if I increase the number of neurons, 10 neurons in one lattice. I have taken a 2D lattice. Okay, so I have placed 10 neurons in this axis and 10 neurons in this axis, right. So, if you increase this neurons to be 100 and this is 100, and this regularization of this structure will be even much more pronounced. You can do that experiment also. So, we can easily again see another video of seeing this. So, you see that earlier the neurons were associated, they had no idea about the input space, and slowly you see that neurons are exactly taking a shape of a square lattice. Okay. So, those who did not see it properly, again for their benefit, again I am repeating the same video. So, you can easily see that how neurons, those who did not have any idea in the beginning, they again take the shape of the actual input space. All right. So, again we go to the other example. So, this is just like we took the square space. Now, again we take a L space, but again 2D lattice. So, 2D sum learns 2D topology, again the same manner we will do it. So, this is L space. So, this is L shape structure, this is the input data. So, this is the weight vector, initial weight vector for of the 2D lattice for capturing the topology of a L shape input space. So, we want to capture the topology of L shaped input space. Now, this is the final structure after learning, and you can easily see the neurons, their topology is like a L shape here, and you can easily see again how this happens in the movie. So, this is what you are seeing is that how neurons in 2D lattice are learning L shaped in topology space. So, you can easily see this is L and this is the other half. So, for those who could not see it, for them again I repeat it. So, you can easily see that so how suddenly this is a kind of structure, this is the structure. That is L shape. The structure of the input space was the L shape, and that has been nicely recognized. And as I told you, we can always improve this one by using more number of neurons for each. So, that's okay. So, what we learnt until now is that we can use Cohen lattice to learn the topology of the input space. The data is coming from which geometry? Is it 3D, 2D, or it is coming from various shape, circle, sphere, L shape, whatever shape, triangular shape, prism swap, we can actually learn from where the data has come, the space of the geometry of the data from where it is coming. So, that is a very nice identification of the feature space. Now, today I will show you which we will be learning later. We have not actually, we are not ready to represent, because this is a very difficult problem. We will learn in this course this specific, but I will just introduce you what is a visual motor coordination problem. Visual motor coordination, normally you see that like for example, I want to manipulate anything. I want to write something on the blackboard. So, there is a very nice, in a biological organism, there is a very nice correlation between visual feedback and the movement of hand, movement of leg. There is this nice hand-eye coordination that we have, particularly the biological organism, specifically for us, the humans, and some higher form of animals also. They have very high degree of, nice degree of coordination between hand and eye, the visual information and the movement of their organs. So, so can we do this kind of things in machines? So, one example is here is that this is a robot manipulator. You can easily see a 3-link robot manipulator, and you can see is that this is a two cameras, camera 1, camera 2. They give the information about the target where this end effector will go, and based on this feedback, where is the target, this end effector has to reach this point. Okay. So, how that can happen? Through learning mechanism. So, this is camera input. So, I have an algorithm, control algorithm, that will give me from that will formulate a map between Cartesian space to joint space. Joint space means theta 1, theta 2, theta 3. So, if I give a specific angle set point theta 1, the base will go to that specific angle. This first link will go to specific angle theta 2, and the third link will go to, second link will go to theta 3. So, once I know what is the Cartesian space, based on that information, how do I actuate theta 1, theta 2, theta 3 such that this end effector reaches this point? That is the problem, visual motor coordination. And more importantly, even more difficult problem is that if this target is continuously moving, if it is a static target, the problem is simple. But if the target is moving continuously, how this will go? Because if it is here now, it will take a step in this direction, and suddenly this has gone somewhere else. So, how this actually can follow even moving target? So, this is the problem. So, two cameras provide visual feedback to the control algorithm, thus help in positioning the end effector to the relevant position. That is the visual motor coordination. So, this is our robot manipulator, 3-link manipulator. So, the idea is actually we want to learn a map from Cartesian space, okay, which is actually now 4-dimensional, because you see that here we used this 2 camera system is a stereo vision system, because if I have one camera, it is very, because a camera, you know that even if I am looking at a 3-dimensional object, I only have in the camera plane, it is only 2D point, a 2D projection of this 3-dimensional object. So, in that sense, the depth perception using single camera may not be properly done. That is why we talk about stereo vision. We have 2 cameras to make sure that we have a proper depth perception of the 3D object, and hence we can actually exactly locate where is the 3D point. So, that is why we are taking 2 camera thing. So, the objective is what? I will tell you what is how do we solve this problem using a learning framework or the type of neural network kind of learning that we talk about. So, I have a Cartesian space here, this is Cartesian space. And this is my joint space. So, let us to simplify, I say this is x, y, z point in the space coordinate, and this is joint theta 1 coordinate, that is the robot manipulator is theta 1, theta 2 and theta 3. So, how do I learn the map from Cartesian space to joint space in such a way the end effector of the robot manipulator reaches exactly the target position through visual feedback? That is the objective. So, what we do is that from the Cartesian space we create a cluster, small cluster, and each cluster we define a linear mapping from the Cartesian space to joint space. So, this is called. So, in a sense what I am saying is that f is theta is a function of x, y and z, or in this context it is f and u. U is the 4 input given by the camera. 2 cameras are there, each camera output is 2 dimensional output. So, 2 camera will give us 4 dimensional output. So, that is u. Given u, how do I go to theta? So, what happens now, I divide my Cartesian space into small cluster, and within each cluster I define a linear relationship using Taylor series expansion from theta, that is theta u equal to theta s plus as u minus ws, where u is the input from the camera, ws is the weight associated with the a specific neuron. That is, what I am trying to do is that, like a Cartesian space is a 3D space. So, I take a 3D neural lattice, a neural lattice which is a 3D neural lattice. Each neuron represents a discrete cell in the Cartesian space, and then within each discrete cell I define a linear relationship using Taylor series first order expansion, which is theta, the theta, actual theta is theta s. This theta s is the specific discrete cell, the center of the discrete cell is correlated to theta s in the joint space, and as is the Jacobian matrix, u is the input from the camera, and ws is the weight associated with the specific neuron that we are talking about, that discrete cell. So, s represents st neuron, theta is the 0 order term and ws the neuronal weight, S is the Jacobian matrix. So, this is the idea of forming a map between input and output. So, now what we are trying to learn is a cluster, that is, we will construct a 3D neural lattice, and this 3D neural lattice first of all must capture the robot workspace, and obviously robot workspace may be a 3D workspace, exactly, you know, a spherical a cubicle. Okay. So, we will now show, so there are two ways we can do the cluster. In one case we can form a cluster formation only in the Cartesian space, and the other case is the Cartesian and joint space together. We can also do that, and after doing that we can actually make sure that how robots move from given a target position, how robot moves, if given a target position, how end effector moves to that target position through learning. So, that is what we will now learn. So, this what you are seeing is that how a 3D neural lattice is learning a Cartesian workspace. You can easily see that the data is coming from Cartesian workspace. Those who could not follow this, again I will do it again. You can easily see now this one, and you can easily see that how the Cartesian workspace is the topology of the Cartesian workspace are being learnt by a 3D neural lattice, alright. So, this is the first one. Now, I will combine the Cartesian space and joint space, and again we will try to form we will see that how that learning takes place. So, you can easily see that the 3D neural lattice learns the workspace of a robot manipulator very accurately, and this is much better actually in this case when we combine the input space and joint space, sorry, Cartesian space and joint space. And finally, using this notion, I will show you how a robot will actually capture. So, you can see this is my target and this is my end effector, and it moves around it, and finally it goes until it exactly converges. You see that now it has exactly converged. So, those who did not follow, I again start this thing. So, you see that this is my end effector and it is going to try to reach this target. So, this goes very close and finally, it has reached exactly, you can see now this has exactly reached. So, using Cohen sum, we can do many things. So, first of all, let me summarize. Before I summarize, let me so using a Cohen lattice, we can do many things. One of the things is that I will teach you in this course how to do system identification. We can easily do system identification and some of the difficult tasks like visual motor coordination. And these two topics we will exclusively take when we go detail into application of neural network in intelligent control. So, let us now summarize what we discussed today. A Cohen sum, the first what we have to do is initialize. We select a specific lattice, Cohen lattice, it can be 1D, 2D, 3D, even higher dimensional lattice, and then we select assign these associated weight vector with each neuron of the lattice randomly, and normally usually the associated vector of each neuron has the same dimension as that of the input data or input vector, and you draw a sample x from the input space randomly, and then excite all the neurons, find the winning neuron, and then after you find the winner, you weight update. This is actually Cohen learning algorithm. This is the sum and substance, which contains a very important item called neighborhood function HJI. As I said you in the beginning of the learning, the neighborhood function is adjusted in such a way almost all the neurons in the lattice, they take part in decision making, and slowly as learning progresses, very few in the nearest neighborhood of the winning neuron, they take part in the decision making. And then we continue the step from 3 to 2 to 4 until the training is over. And finally, when training is over, we can easily see that a Cohen lattice has actually learned the topology of the workspace. Thank you very much.